Namaste dosto. Imagine you're standing somewhere on a vast field and you want to find the shortest path to reach a straight fence line ahead. Naturally, you walk straight towards the fence, crossing it at a right angle, because that's the shortest distance. This simple idea is exactly what we call the perpendicular distance from a point to a line. In coordinate geometry, this perpendicular distance represents the minimum distance between any point and a given straight line. It's measured along the line that meets the given line at a perfect right angle and passes through that point. Now, suppose the line is represented by the equation ax plus b y plus c equals 0. Here, a, b, and c are constants defining the line, and the point is at coordinates x1, y1. The perpendicular line segment dropped from point P to this line is the shortest route you can take. This concept isn't just theoretical. It plays a crucial role in real-world applications like optimizing routes, designing buildings, and projecting shadows. Even if you change the coordinate system by rotating or shifting the axis, the perpendicular distance between the point and line remains unchanged as long as their relative positions stay the same. Remember, we use this distance to understand how far objects are from reference lines, to detect positional errors, or to calculate the closest approach between moving bodies. Isn't it amazing how this idea of shortest distance connects geometry to practical problems all around us? चलिए, अब इस कॉन्सेप्ट का एकदम गहराई से ब्रेक डाउन करते हैं. Suppose we are given a point P with coordinates x1, y1, and a line written as ax plus b y plus c equals 0. The perpendicular or shortest distance, d, from the point to the line is given by the formula. D equals the absolute value of ax1 plus b y1 plus c, divided by the square root of a squared plus b squared. Here, the numerator represents the absolute value of the scalar projection of the point onto the line's normal vector. The denominator is simply the magnitude of the normal vector n, which is written as open bracket a, b close bracket. This result comes directly from vector projection and normalization principles in Euclidean geometry. And importantly, the formula works in all cases. If the point lies on the line, then ax1 plus b y1 plus c equals 0 and a distance comes out to be 0. Let the line L be written as ax plus b y plus c equals 0, and let the point P be at coordinates x1, y1 in two-dimensional space. Now, choose any point Q on the line such that Q, with coordinates x0, y0, satisfies the line equation. The normal vector of the line is an equals open bracket a, b close bracket. The vector from P to Q is written as PQ equals open bracket x1 minus x0, comma y1 minus y0, close bracket. Next, project the vector PQ onto the normal vector n to get the perpendicular distance. That gives D equals the absolute value of PQ dot n divided by the magnitude of n. Finally, when we substitute and simplify, we arrive at the standard formula. D equals the absolute value of ax1 plus b y1 plus c divided by the square root of a squared plus b squared. And that is the perpendicular distance from a point to a line, derived using vector and coordinate geometry. If the point lies on the line, then the distance evaluates to 0. Because ax1 plus b y1 plus c equals 0 directly implies d equals 0. The value of the linear expression ax1 plus b y1 plus c determines which side of the line the point lies on whenever the value is non-zero. In fact, we can even assign a sign to the distance expression without using modulus to encode sidedness in geometry, like left or right, above or below the line. This sign distance is critical in applications such as classification using line equations, or in computing minimal distances for optimization problems. Finally, the line can also be written in what we call normal form, a prime x plus b prime y plus c prime equals 0, where the coefficients are scaled in such a way that a prime squared plus b prime squared equals 1. We are given the point P at coordinates 3, negative 2, and the line 2x minus 3y plus 4 equals 0. We want to find the perpendicular distance between them. Let's substitute into the formula. D equals the absolute value of 2 times 3 minus 3 times negative 2 plus 4 divided by the square root of 2 squared plus negative 3 squared. That simplifies to the absolute value of 6 plus 4 divided by the square root of 13, which is 16 divided by square root 13. Now for the approximate value. Square root 13 is about 3.606. So D is approximately 4.44 units. Finally, notice that the numerator was positive before taking modulus. This means the point lies above the line on the positive side of the linear expression. To wrap up today's lesson, let's quickly recap the key formulas and ideas. First, the absolute distance formula. D equals the absolute value of ax1 plus by1 plus c, all divided by the square root of a squared plus b squared. Second, the sign distance formula. D signed equals ax1 plus by1 plus c over the square root of a squared plus b squared, which tells us on which side of the line the point lies. Third, remember that the normal vector of the line is a, b. The main takeaways. The distance is always measured along the perpendicular. It's the shortest path from a point to the line. This calculation is deeply rooted in vector projections. The sign of the linear expression ax1 plus by1 plus c informs us about the relative position of the point with respect to the line. And the inverse square root term relates to the magnitude of the line's normal vector connected to the line's slope.